As x is going to negative 1 for k of x, you can see that that's where the joint is, where the split is. So that means we have to check both sides. If x is going to negative 1 from below, from the left-hand side, that means we'd be on this domain, which means we'd be on this function. As x approaches negative 1, this function's approaching negative 3. So, although it doesn't ask for it, if it's at the joint of a piecewise function, we need to check the left and right hand limits. And from the left, this thing equals negative 3. From the right of negative 1, k of x is approaching. Well, now we're on this interval, which means we're on this function. As x approaches negative 1, it approaches what this graph equals, which is positive 3. Since they are not the same number, this does not exist. Okay, and again, what that means is you can see on a graph at 1, here's negative 1, the left-hand side, 2x minus 1, is headed towards negative 3. So it's doing its best, it's coming up here, boom, it gets to negative 3, and then my rule says stop at negative 1, jump to this function. Well, this function starts at positive 3. 1, 2, 3, and goes off like this. And since x can equal negative 1 on this function, that would really fill in this dot. So that's what this graph looks like at negative 1. So the limit doesn't exist. I can't zoom in on the x value of negative 1 while zooming in on a y value. It doesn't happen because the y values are up here on this side and down here on this side. All right, as x goes to positive 1, now as x goes to positive 1, we're on this interval the entire time. X equals positive 1 is in the middle of negative 1 to 3. So as x approaches 1, k of x should be approaching what x plus 4 equals, and that's 5. All right, as x goes to 3, now that's where the joint is at 3. So we've got 1, 2, 3. There we are. As x approaches 3 from the left, so let me change these guys up some. We're checking both sides now because it's at the joint. As x approaches 3 from the left, and 3, positive 3 here, okay. 3 from the left, we would be on this interval because we're less than 3, and k of x should be approaching what this equals, which is 7. So from the left-hand side, this function is headed towards 7. I don't know what happens after it gets there. So this is 3, 4, 5, 6, 7. Okay, I don't know what happens once it gets there because it says stop at 3. Okay, it doesn't equal 3, so we just stop. There's an open circle on that graph. And it tells me at 3, this graph equals 1. So at 3, the function is 1. That's a dot there. And then when x is greater than 3, we're on this function. Well, when x is 3 here, this thing starts when x is 3, which is 9 minus 2, which is 7. But it does not into an equals 3, so it'd be an open circle, and then it's a parabola going upwards like this. Okay? So that's what this graph looks like. A very rough sketch, but that's what it looks like. So as x goes to 3, you can see if we zoom in on 3, both sides of this function are getting super close to 7. Which I didn't write that down here, but they're both getting super close to 7. It doesn't get to 7, but remember, the limit doesn't care what happens at 3. It cares what happens around 3. And around 3, this function's getting close to 7. The limit as x goes to 4. Well, at 4, we are entirely on this interval. It's not a joint. We're just 4 is greater than 3. So this function is approaching what x squared minus 2 is approaching at 4. And that just means what it equals since it's just a nice function for us. And that's 16 minus 2, which is 14. Where is k of x discontinuous? Well, the graph really helps us see that very much. It's discontinuous at negative 1. Okay. I'm blowing up. Let's see who it is. Oh, it's the president. Let me talk to him. Hello, Mr. Obama. Oh, you need math videos? Oh, I can't believe it. I'm working on it right now. Yeah, piecewise functions, exactly. That's going to stop the terrorists? Oh my God, I am a national treasure. I agree with you. I agree with you completely. Nope, I can't do them all on the phone with you, Brock. Come on now, stop yelling. No, almost done. Okay, talk to you later. Bye. Okay, it's tough being a math teacher. Where is k of x discontinuous? Well, at negative 1, it's discontinuous. You can see that here as a jump. And that's happening. You can tell, even if we didn't have the graph, you can tell it was happening because at negative 1, the limit didn't exist because we checked both sides. One side was going to negative 3 down here. The other side was going to positive 3. So it's not continuous there. So it's not continuous at x equals negative 1. And it's also not continuous at positive 3, because although the function is approaching the same number from both sides, the limit exists at 3. We got 7. The limit exists. But when it gets there, the function's way down here. So it jumps down to here and then goes back up. So it's also not continuous at 3. On what intervals is the function continuous? Well, it's continuous everywhere. It's not discontinuous, and it's defined. Well, it's defined everywhere because all this graph is a collection of, it's a line, a line, a line, and a parabola. Well, they're defined everywhere. And as long as I have all x values accounted for over here, which we do, then this thing is defined everywhere. So it's continuous everywhere that it is not discontinuous, which is -1 and 3. So you can say it's continuous for all real numbers, except x can't be -1 or 3. Some teachers don't like that. They want to see interval notation, so you could also write it like this. It is continuous from -infinity all the way up to -1, union with all numbers from -1 to 3, union with all numbers from 3 to infinity. So this is a possible answer, this is a possible answer.